Okay, so everyone is really interested in what on the first exam will be, and according to my detailed calculations, we don't have class this coming Monday, right?
No.
I mean, I'll show up if everyone else shows up, right? No? So we're on 5 today. That means we'd get through 10 by the 17th, and then the test would be a week later on the 24th. Any objections so far? If you guys have a major conflict with another test in another class, let me know. Strangely enough, I don't want to test you on your ability to go without sleep. So if there's another exam on the same day, we can be flexible.
So funny, we got exams like every day this semester so far.
Every day of the semester, really? Wow. That first day exam must have been a killer.
It was awesome. What's your name?
Yeah. Hopefully I already passed that one. All right. Okay, so send me an email if you spot a big conflict with that. All right. Let me know. Okay. Any questions, comments? I asked before about Carmen. I'm assuming the lack of response is that Carmen's working great. You guys can access the lectures. Everything seems to be all right. You can hear me well enough on the recording. All right. Okay. We're good to go then. All right. So today we're going to start talking about, first off, the broad class of just polyolefins. And I wanted to bring this up because it's a word you sometimes see. I think this is something that chemical engineers use a lot, but I just wanted to give you this as background. These are materials that are based on the polymerization of carbon-carbon double bonds. So let me go with a more interesting color than that. Or alkenes, for those of you who had organic chemistry, which basically means a lot of what we talked about. Okay, so polyethylene, of course, polypropylene, and then we can get into other names here that you fortunately don't have to memorize. Polymethylpentene, there's elastomers in this category, polyisobutylene, we'll talk about that, and ethylene propylene rubber, we'll talk about that later on, and then ethylene propylene diene. There's an M class of rubbers, EPDM rubber. Some of you may have heard of that. That's a pretty important compound for a lot of different reasons. These are all based on this process of breaking open this double bond, causing polymerization to occur with that as the monomer, and then adding on to the growing polymer chain using that particular route for polymerization. And perhaps unsurprisingly, because we talked about this as being a characteristic of polymers, is that these are difficult to join by techniques such as solvent cementing because they have what we want them to have, which is excellent chemical resistance. All right, so this is something that is an outgrowth of the fact that these resist a lot of solvents. Let's see, the one that I always think of is PVC. Has anyone ever had joined PVC pipe? You get that purple gooey stuff and you use it to join the PVC to another hunk of PVC. That's got tetrahydrofuran in it because I know how it smells. And so I recognize that smell whenever I use that crap. All right, and that's a pretty powerful solvent, and that's what's necessary to try to soften the surface of that PVC enough so that the polymer chains from both interfaces cross over and form a permanent joint. It's probably a lot of it's the plasticizer, by the way, not so much the PVC. But anyway, so these are the kinds of things that we have to deal with, and in many cases, we talked about this with polypropylene. You can only bond them after surface treatment, meaning that you etch the surface and make it chemically active because they otherwise have very low surface energies. Okay, so this is something that, again, it's all an outgrowth of why we have plastics in the first place and what they allow us to do. All right, so we're going to pick up kind of where we left off from before with the issue of constitution, which is what polymers are made of, what goes into their chain structure. Everyone read this well enough? Yes? Okay. I changed the configuration here on the screen a little bit, but I'm not sure. I might like the other one better. Anyway, but so what we've been talking about to date has been this first category, in which we have hydrogens around a carbon, And we can also talk about PVC in this context. And this is called head-to-tail configuration. I'm highlighting the chlorines just to make it more obvious. All right, and so what we have are two monomers which are originally double bonded. All right, so polyvinyl chloride means we start with vinyl chloride, which is, we talked about ethylene gas. This is just the same thing, but with a chlorine in there. So those double bonds bust open via temperature and pressure and catalyst, and they start to very rapidly form these chains. Remember that the problem they had was that back in the 20s, when they first started making this stuff, they didn't have good control over the purity, unsurprisingly, in 1920. And so the stuff, these reactions would just take off and blow up. So it was kind of a hazardous thing to do work in this area. But anyway, but what you're looking at is that the chlorine is separated from the other chlorine by an intervening carbon. All right? And hopefully, based on the discussions we've had to date so far, what I'm about to draw will make no sense to you. If we instead produce a head-to-head configuration, that's what head-to-head means. All right, so first off, head-to-tail is the normal one. All right. What do you see that's wrong with the head-to-tail? Yes?
Are the chlorines too big and they're both negative, so they like affect it?
All right, you got both answers. Okay, great. So yeah, they're much too big. These are not tiny little hydrogen protons. All right, chlorine's much higher up in the periodic table, and they're also very electronegative. All right, that's what enables hydrogen bonding. So these guys are going to physically hate each other, and in terms of electrical charge, they're also going to hate each other because they're both negative, they're both big, and so this is probably not going to form. I'm drawing it anyway, but what I'm trying to do here is say that this is how we distinguish between these two configurations, and while this may be difficult, it's not impossible, but difficult to do, for something like polypropylene, you can have the same, you can have head-to-head polypropylene if you want to, but in most cases it's not made that way. All right, everything typically, because of either this electronegativity issue or the steric hindrance issue where the side groups bang into each other, you usually get head to tail. All right, any questions about that? And then something we've already talked about somewhat is this tacticity issue. And in this context, it starts to become important in terms of how many polymer chains you draw, or how many units in the polymer chain you draw. And so in this context, we have the chlorines on the same side, and I'm picking on PVC because it's the fastest thing to draw. But you can think about this for polypropylene or polystyrene or anything else, but this is just illustrating concepts, and this is the easiest way to do that. And so this is isotactic polyvinyl chloride, all right, and isotactic polyvinyl chloride can crystallize. Why? Because all the puzzle pieces are the same no matter where you look. So you get crystallization in this context. And then we have the opposite case where the chlorines are on opposite sides. So that's supposed to be a Cl again. You guys.
With the intervening carbon in the middle, does that matter as much, like stability?
Does the carbon in the middle matter in terms of what?
Does this matter as much as the homopolymers in terms of stability of the structure?
Well, the carbons provide stability. They hold everything together. I mean, this is a very strong bond. Carbon-carbon bonds are very strong.
I'm saying, is there too much of a difference in this between these two structures and stability?
Oh, chemical stability.
Yeah.
Oh, no, there's not a whole lot of difference here. All right, they're far enough away from each other. The hydrogen is in between them that they're happy in either configuration. Okay, they do have slightly different melting points, but they're pretty stable compounds in either case. And so this is syntactic, which means opposite sides, and this will also crystallize. Why? Because all the puzzle pieces are the same in every direction. If I shake this, does it do something? So that, oh, there it goes. I don't know how I'm doing that. Then there's the alternative, and this is something that first off requires a certain number of carbons to really demonstrate this. And I am not going to put the hydrogens in, which on a test you are not allowed to do this. You have to draw the hydrogens. So here we have 2 chlorines on the same side, and then we pick one up on the opposite side, and then we pick another one up on the same side as the others, and if we wanted to, we could do something like this. All right, so there's some isotactic ones, and again on the test you guys have to put all the hydrogens in. Okay, but the point being that if you just zoom in on a couple of carbons, it looks isotactic or it looks syndiotactic, but to really do it justice, you have to have enough carbons to demonstrate the fact that it's atactic, that there is no fixed structure as far as the arrangement of chlorines. And so the key difference here is that in the case of this being atactic, as I just tried to demonstrate, and I know it doesn't look dramatically atactic, but 1 chlorine on the opposite side is enough to help prevent crystallization of these materials. All right, so think beyond this. The next 10 carbons, some other arrangement of chlorines randomly arranged around that main chain. Okay, so as we talked about before for polypropylene, this will give you atactic materials. And atactic materials, okay, I think I like this one better. Except it won't hang on to it. That's weird. It's going to give you something that gives you different mechanical properties, because when you take away all that crystallinity, then it becomes a softer material, a less brittle material, a more easily deformed material, and so crystallinity is pretty significant in terms of controlling properties. So if you engineer it so that it can't crystallize, you're going to engineer a very different property set. And again, keep in mind, if I ask you to draw something as atactic on a test, crank out 10 carbons. All right? Keep that in mind. Okay, so as I've already mentioned, tacticity has strong effects on crystallinity, and then this issue of packing, as I keep hitting you with, the puzzle pieces, they need to be similar. And if they're not, then we frustrate crystallization. And this is very much like atomic packing. And the idea again also that's similar for inorganics is that enough strain can be present if we're trying to accommodate a really big interstitial atom in some inorganic metal structure or ceramic structure. It can prevent the process of crystallization because it just doesn't allow it to happen. And the same is going to be true for polymers. So again, now I'm going to give you a little more detail here. So what I'm doing now is I'm drawing the bond angles, and this is necessary because this is part of the crystallization process. And so we have these bond angles, and these chains have to line up with each other. Okay, and they also need to have, let's just say this is isotactic PVC. All right, and everywhere else is hydrogen. Etc., etc. Okay, and so hydrogen's down here as well. Okay, so given what we just talked about a minute ago, this configuration should make sense. First off, the chlorines, everything's lining up, all right? So this overall structure is going to be crystalline because all the puzzle pieces are the same. They point in the same directions. The chlorines are lining up, but they're also on opposite sides of the carbon chain from each other, so that the repulsion issue doesn't really rear its ugly head and make this thing impossible. But if I then turn around and I have a chlorine here and a chlorine there, all right, so this little piece of the chain is probably not going to crystallize. Oops, hold on. I didn't mean that. Habit. This guy's pointing down, pointing the wrong way. All right, so now this part of the chain is probably not going to crystallize because the puzzle pieces there are different. All right, and so this points out a couple of things. One, that you can have a little bit of irregularity in the polymer chain. You still have crystallinity elsewhere, all right, as long as enough of the length of the chain lines up to enable crystallization to occur. It will tolerate defects. We'll talk more about that when we go into more detail about crystallization later. But this is something that can be tolerated and doesn't kill off everything else as far as crystallinity is concerned. And the other effect is that the presence of this amorphous polymer that has this strain associated with it is going to decrease the melting point. All right, so that strain is going to make the polymer crystal more easily dissolvable back into amorphous polymer. All right, and hopefully that makes sense. Yes? No? Okay. So and think about this is that and I'll bring it in now. I'll talk about it again later. But heat in the polymeric world is not heat. It's motion. All right. So this gets hotter. The chains vibrate faster. It gets cooler. They vibrate slower. All right. So polymers don't experience hot and cold. They experience vibration, more vibration or less vibration. And so in that context, we try to heat this up. If there's a defect, it's under strain, it's going to start falling apart more quickly. And it may also influence its neighboring crystal structure. Any questions about that? All right. And so at this point, now that you have some rough idea what polymer crystals look like, I want to ask the question, why do polymers crystallize? And this is something that illustrates another dramatic departure from the inorganic world. Similarity is, of course, delta G still equals delta H minus T delta S. All right, that's still true. Now, in the inorganic world, this term says, not important. We don't care about entropy in the inorganic world. Not so for polymers. We do know, as before, to move a reaction forward, you want to minimize the delta G associated with that reaction. All right, so make it as negative as possible, if not zero. We also know from what I just told you, and you guys had this on the concept test, is that random chains provide the maximum entropy. Okay, so what that means is when you take those random chains and turn them into a crystal, that's going the wrong way as far as the entropy is concerned, because you've now fixed them in one configuration inside this structure. They're locked in that what I just drew in the previous slide. And so they don't like that from the standpoint of randomness and maximizing entropy and minimizing energy. So from that perspective, this crystallization should never occur. Okay, so this will decrease the delta G, make it less negative. Thus, this crystallization is not favored from a purely entropic point of view. However, keep in mind that unlike organics, for polymers, entropic considerations are often dominant. Now, so I'm giving you an exception to this rule, but keep it in mind that polymers over and over and over again try to maximize their entropy. But in this case, when crystallization does occur, which it must, or else I wouldn't be talking about it, some random chain is converted into a regular array, which is causing this problem with the energy system, the free energy system, but it's a delta H term here as well, and so we are increasing that order, but we're also decreasing the enthalpy and it turns out that the delta H is larger than the T delta S. So T delta S goes in the wrong way, the delta H goes in the right way. So this is one of the rare cases where enthalpy wins, all right, over entropy in this context. In many, many, many cases, we'll talk about this, entropy usually wins, but in this case it doesn't. But for the right type of polymers under the right circumstances, the free energy of the system decreases and crystallization is favored because of the enthalpic change. Okay? Any questions about that? So you get an idea why we consider randomness and entropy to be so important. The joke I've often heard is that on a test question, the best thing to do is write the word entropy and then try to figure out how that answer is connected to the question. So anyway, but the entropy is very important in this class because it's very important in terms of how polymers behave. All right, so once we have crystallinity, how does this compare to inorganic unit cells? And so this is an example of an inorganic unit cell. It's a fluorite structure, so it's like facing in a cubic but with more atoms stuffed into it. All right, and so we know, kind of from the previous discussion, if I take these atoms and I push on them, all right, it's possible for them to slip down a given plane, shift over, and become part of a different unit cell, right? It's still crystalline after it's made that slip, that dislocation's gone through it, and I can get the same slip to occur along an entirely different direction with the same level of resistance, because it's a three-dimensional structure, the same in every direction, and that's just the way inorganics are. They're bonded in all directions inside that unit cell. If we instead look at polyethylene, which is obviously a lot more complicated, this helps simplify things a little bit. You kind of look down on one central plane in the unit cell, and you can see the different components, carbons and hydrogens and so forth. In 3 dimensions, though, it looks like a big mess. And so in this context, going back to discussion from before, if I push on one set of chains and another set of chains, then I can get slip maybe between them, okay, and that'll have a certain energy. But now if I try to do the same thing I did on the inorganic cell and I push from these directions, then we have these polymer chains that are going to resist that process very, very strongly. Again, carbon-carbon bonds, in the majority of cases, they're not going to break. All right, there's a few that we'll talk about where that does happen, but in general, when we talk about the behavior of plastics, we're not talking about polymer covalent bonds breaking. Okay. Any questions about that? And we have van der Waals forces holding everything together. Over here we have ionic in the case of a fluorite salt, or covalent in the case of a metal. All right, or a metal carbide. And one of the other key things, this is an inorganic unit cell. What close spec structure is this? What? BCC. How many atoms are in that structure? 2, right. 8 eighths and one in the middle. Okay, you guys remember having to do that before? They still force you to do that stuff. How many atoms in an FCC cell? 4, yeah. So it's 6 halves and 8 eighths. So 4 in a FCC, 2 in a BCC. In contrast, if we come over here, I think this is bismaleimide, it's a high temperature polymer. There's a lot of atoms in that unit cell, all right? Not just 2 or 4, more like 40, all right? And this doesn't even show all the hydrogens. Okay, this is just the carbons, and I think these are double bonded carbonyls over there. All right, so there are a lot of atoms in a unit cell in a polymer. All right, so fortunately, we don't have you go through the exercise of trying to divvy up and count fractions of those atoms. So you can have hundreds of atoms in a unit cell when it comes to something that's a polymer crystalline. Everyone see that? Huge differences there. We have with the inorganic cell, it's made up of isotropic cells, FCC, BCC, and this is an example of an important ceramic material, magnetite, FCC. And again, the same thing holds true here. You can you can force dislocations through this. So Fe3O4 would be kind of hard to push a dislocation through, but in theory you could do that and get this shearing to occur along a given direction between that set of strained crystal structures. But again, going back to what I said before, but more in 3 dimensions, the chain directions control the cell properties, and you get anisotropic properties as well. So again, it's not going to respond to what we think of as FCC and BCC, because that doesn't really apply anymore. The chain directions are the strongest directions in the unit cell by a lot. All right. What polymer is that? The white is oxygen, the gray is carbon. This is not a test question. What? PET. Good. All right. So this is not something you'll have to do on a test. The hydrogens are not drawn, and so we have double bonded carbonyl oxygen, and then that ether oxygen in the chain, and then we have a little chunk of polyethylene, and we go back to another ethyl oxygen, carbonyl oxygen, and then we have that big phenyl group in the middle. All right. But again, in this context, when you put all that in a unit cell, then the chain directions are the strong directions, and we'll talk. That becomes more and more important as we talk about polymers. Any questions about this so far? All right. So what I want to do now is talk about molecular conformations, and this is important because I'm getting ready to talk more about polymer crystals, and this was something that marked, back in the day, a period of uncertainty about plastics. And so we had all these polymers burst onto the scene, and brand new materials, and they started making toys and dinosaurs and rulers and replacing wood and everything in all directions, but we didn't know a lot about what their structure actually was. I stand here and talk about crystallinity, but back then we were manufacturing things by the millions, and we didn't know about polymer crystals. Right? We didn't, unlike what we expect from metals and ceramics, where you have big old grains. These don't have big grains, and they're very hard to see in a melt-produced plastic. So they do exist, but they're teeny tiny, 2 to 5 nanometers thick and maybe 20 nanometers on an edge. They don't respond well to fractography. I know you guys have maybe seen the issue. You break an inorganic and you see intergranular failure or transgranular failure, and you can learn things about the material. With plastics, you do that, you don't see anything like that. There's nothing that big, first off, to begin with, and the crystals that are there are too tiny to show anything in fractography. And this is the 1950s and 60s. SEM had just been invented back then. I think the turn of the 50s they invented SEM. So we didn't really have tools to see these things. We didn't have TEM, that's for sure. And so what they did was they started looking at a process called solution crystallization. And you'll see some products of this in the next lecture. But first we're just going to talk about how we get to the growth of these large crystals, because it also relates to issues involving entropy and the idea of how do we dissolve polymers in solvents. And so we're preparing for discussions of polymer crystals, and then as well getting some idea of when plastics have an issue with solvents, which typically not water. When they do have an issue, what's going on? First off, these things have to be very dilute solutions, and the goal of this dilution, so it's like 0.01 weight percent, really tiny amounts of polymer dissolved in a solvent. You want no polymer-polymer interactions and only polymer-solvent interactions. And so what you've got, this cartoon is showing you this as 2 very lonely polymer chains. All right, so they are dissolved in solution together, they're not touching each other, and they're only associating with themselves. And so you have to have this in order for this process to occur, which we'll talk more about later. And this effective concentration is such that, so over here on the right, all right, so this would be one potential way of thinking about a polymer melt. A whole bunch of polymer chains, they're all entangling with each other, all right, which has effects on mechanical properties, and they're not lonely, all right. They are just intertwangled with themselves and their neighbors, and in that context, you're not going to get large-scale crystallization. You might get tiny-scale crystallization, but you're not going to get something that you can see in an optical light microscope. All right, so over here is what we're talking about, where these polymer chains are kind of coiled up together and they're not able to touch each other. And remember that if we zoom in on those polymer chains, they look like spaghetti, but they still obey certain laws as far as bond angle if you zoom in on them. And then this in-between state, they aren't quite as lonely there. This is not good as far as crystallization either. So you really need to be over here on the far left-hand side, where the polymer chains are seeing 99% solvent and, hopefully less than 1% polymer.
What concentration is?
Oh, that's the critical concentration for nucleation and growth of a polymer crystal. All right. But that's, we'll talk more about that later. The goal in this context is to first off have no net attractive forces between the different coils as they sit in solution. And because of this, we get large conformational differences from the solid state.
What is
Question?
the C star again, like this?
C star. And the point here is that we generate what's called the 3-carbon model. So that is critical to this. C1, C2, and C3. And so C1 and C2 are fixed. All right, so these two guys are stuck. This is just for illustration purposes. They can't do anything relative to each other. C3, on the other hand, first off, it does satisfy the bond angle of 109.5, all right, sp3 hybrid bonding. So it has that angle, but C3 is able to rotate around C2 star. It's not fixed. And so what that means is it can rotate around C2 while still having that 109.5 degree angle bond. And so in doing that, it's going to, if it rotates, it's going to be able to rotate through a cone. I don't know if you can see this in your mind's eye. So this is my cross-section of a cone. So that C3 rotates around C2, and it keeps rotating and maintaining that 109.5 degree angle the whole time. Why is this important? Because this is the kind of benefit that being in solution gives us. In a melt or in a solution that has too high concentration, this can't happen. Right? It bangs into its neighbors and can only move just a little bit. And so this conformational freedom and the very large entropic freedom means that it can continuously change its position very easily and help facilitate this process of crystallization. Real polymers are not truly freely jointed, but there is, however, free rotation around the chain bonds, as you're seeing here. So in the real world, of course, C1, C2 are also able to rotate. Okay, so if you start thinking about all those angles and the fact that this can go through 360 degrees of rotation around its neighbor, you can see there's a lot of flexibility if you take away the neighbors that prevent those polymer chains from moving like that. Any questions? So first off, the thing to think about is that in solution, polymer chains exist as coils. All right, they don't exist as individual polymer chains. Let me rephrase that, not as stretched out polymer chains. So we draw that a lot in class. In the real world, polymers don't like that because in a coil, there are an enormous number of different ways in which a chain can be curled around in a compact state. That means we have an enormous number of configurations, a very large number of configurations, and that is the definition of entropy. So the more randomness, the more coiled-like structure you have, the more different configurations you can have on a local level, which means the entropy is maximized, the energy is minimized. And so polymers exist as coils, and the computational shape is actually kind of a kidney bean shaped coil. And that's apparently the way that they like to exist in solution when they're by themselves, certainly. There are comparatively few ways it can be stretched out. So if we think about taking a polymer chain, and there are ways of doing this, and just stretching it out so that it's kind of mind's eye a string, a straight string, how many configurations are there? One. All right. Polymers hate that. All right. They only have one configuration. You just minimize the entropy and maximize the energy. So this is definitely difficult to do. It's possible, but they don't, under normal circumstances, do this at all. Okay, if each conformation has an equal probability, chains are much more likely to be ball-like than they are to be extended. And this is, again, an entropic effect. And the structure is driven by entropy. The shape of any one chain will have most of the time. Again, they're not freely jointed, but again, we have all this free rotation around all these carbon-carbon bonds, and so it makes sense that it can easily respond to those entropy drivers and coiled shape. And in this context, if N monomers form the polymer, we talked about degree of polymerization, same thing is holding true here. Its total unfolded length, which it never likes to do, is L, which is equal to the number of monomers times the length of each monomer. And then there's this concept of average end-to-end distance, which, as it turns out, is equal to the square root of capital L times little l. We'll talk more about what that means later on in the class. It has to do with the ends of the polymer chain and how far apart they are from each other. All right. It's not the total length, which is what you might think when you first see this term. But what I really want to talk about is a different term, which is called the radius of gyration, which you saw a minute ago anyway. R sub g is equal to the square root of capital N, the number of monomers, times that length of each monomer divided by the square root of 6. And when we talk about and compute R sub g, this is showing you the radius of gyration for bovine serum albumin, a biological molecule. And that's what you're seeing here. These guys are amino acids that make up that protein. And if we compute the radius of gyration, it's this pink sphere. That's R sub g. Okay, and so that is the average diameter of all the components of that polymer chain. But you see things that are outside of that R sub g. It's just looking at the average position as a function of time, saying, okay, this is about where the average diameter is going to be based on everything that's in that polymer structure. Okay, and so that's how we think of polymers in solution, is following that rule. And where this becomes important is, an example here is in nanocomposites. And so if we have a lonely polymer chain that is held between two plates that are very far away from it, first off, so it's very lonely, it doesn't have to worry about the plates. If we start to squeeze those plates together, then that individual polymer chain starts breaking up into individual coils. So this is the same as that initial chain, but now it's being squished by these plates that are starting to confine it. And so instead of being one blob, it kind of breaks up into many blobs instead. And then finally, if we bring things really close together, then we can actually destroy the coil structure altogether. And we also then produce a very intimate association between the polymer chain and the plates that are squeezing in on it. And so what this does is it gives us a sharing of properties that's very, very intimate, very well mixed. Okay? And this is how Toyota makes timing belts using clay nanoparticle particulates and nylon. And they mix those together and they crank out these timing belts that are based on these nanocomposite technologies. All right, this is part of the interest and excitement about nanocomposites, is being able to squeeze things together and get very good load sharing between them because you've made them very, very well mixed in this structure. But you start with R sub g and you squish it, and then try to get this very close association. All right, so this is the goal, and the question is, how do we get there with polymers? And the rules here are a little different than what you're used to, which is what I'm showing you here. So thanks to our chemistry department, you guys should have this overall picture of dissolution. They focus on the inorganic side of things. And you guys have all heard the rule, like dissolves like, right? That's still something that's important in chemistry. With inorganics, it's also important with polymers. So if I have polystyrene, anybody have a guess about what solvent will dissolve polystyrene? Yes? No, it doesn't really do a very good job with it. But look at the side groups of polystyrene. What do the side groups look like if you think about a molecule? What?
Water.
Chlorine?
Water.
Water? No. Yeah, fortunately, water doesn't do anything in polystyrene, else it wouldn't be a very good cooler material. So that phenyl group, right? We have that in benzene, or we also have, toluene. These are two solvents. You guys are probably not familiar with them. Benzene is extremely bad for you. It used to be back in the 50s at machine shops, they would wash their hands in benzene inside. And now it's banned from everything because it's such a potent carcinogen. Okay, so benzene will dissolve polystyrene, toluene will dissolve polystyrene, acetone not so much. Okay, it's like dissolves like. In the context of what you're used to seeing, so if we have salt, we start with salt, sodium and chloride, we put it in water, okay, and what's going on is we have a very strong attraction between sodium and chlorine. We saw the fluorite structure a minute ago. Those guys are really well adhered, and they come into contact with water. And water does what it's supposed to do. We talked about this last lecture as well. We have an interaction between the positively charged hydrogens and the negatively charged chlorine, and the negatively charged oxygen and the positively charged sodium. So those go in there and they start breaking up this crystal structure, and ultimately you end up separating these two. So the water runs off of the chlorine and the water runs off of the sodium. It forms coordination spheres. They still teach you that? I don't know if they do that or not. Okay, so you have an inner layer of water, and then outside that you have another layer of water, and then you can have a third layer of water, all based on how the oxygens and hydrogens are coordinating with each other. And so these spheres of solvation have taken these two atoms and pulled them away from each other, and now we say they are dissolved at that point because they're no longer associated with each other. So this is how we're used to thinking about dissolution. But a polymer, however, is similar in some ways, but it's also very different. And instead of the enthalpy of dissolution, which you guys probably had to calculate in chemistry, we think about entropy as being the driving factor. And so what we're doing is we're taking that polymer chain that's in a solid, and we're saying, let's put you into a solution where there's infinite ability to move around. And the polymer chain says, great, I can assume all these different configurations I couldn't assume before, maximizing my entropy, minimizing my energy, and so there's a very large delta S greater than 0. We do have to think about what are the relative attractive forces in this context, which is why acetone will not dissolve polystyrene, but benzene will, because again, like dissolves like, and these solvent molecules can find something they like inside that structure. But we also have another factor that's complicating everything. If we have an interface between a liquid and a solid, and we have polymer chains in the solid, and we have a bunch of solvent molecules out here, all right, we can think about trying to go to the point of starting to pull that polymer chain out. So a bunch of it's still here, and now some of it has started to come out. However, even though this small piece of it may be sticking out in solution, net diffusion away from the surface cannot yet occur, so it hasn't actually dissolved. The polymer chain just started the process of dissolving, but it's not dissolved. It's still, most of it in this context is trapped inside that solid. So it's a lot more complicated than salt, where you have just two atoms, they split apart, and you're done. here you've got to think about that polymer chain. Is it going to come out, and then is it going to keep coming out? Any questions about this so far? Make sense? So it is very different from what you're used to seeing with the inorganic world. And so we have this process by which the solid and the liquid are interacting with each other. So we have polymer chain starting to come out a little bit more, and as I drew you a minute ago, we have solvent molecules out here. And if the polymer likes the solvent, it's pretty good odds that the solvent likes the polymer, and so you can get solvent molecules that will sit inside the polymer. And this is kind of helping the process go along, and it should make sense. You know, we have, again, if you have benzene and it's going into the polystyrene, it's finding lots of other benzene molecules to associate with, it makes sense that it should go into that structure. All right. Meanwhile, you know, dissolution is kind of occurring, but what can happen is you can have the process proceed to the point where a lot of that polymer chain has come out, but it might stop. It could also have the situation where the delta S keeps decreasing, delta G equals 0, and then you can have dissolution that may stop in that the polymer has said, you know, I've kind of maximized my entropy already. There's no more driving force for me to come out of that structure. All right, and that you can engineer that process with certain types of materials. The rate of energy gain slows. It could stop. Solidation dissolution occurs below the surface, and as I said, if it's sufficient enough, it can get rid of the driving force. All right. And you often, with a lot of polymers, penetration may only result in swelling, and nylon is kind of famous for this. So you have this process of a liquid-solid interface and polymer chains in the solid, and it picks up a bunch of solvent molecules, and that's it. Cross-linked plastics will do this too. Because they're cross-linked doesn't mean they don't like that solvent. Solvent can go into its structure. They can't come out because they're three-dimensionally cross-linked, but you can get this issue of swelling, which usually means the plastic is not going to work anymore because now it's got this layer of jelly that consists of both polymer and solvent on that surface. So that's kind of the end of that plastic in terms of any type of load-bearing application. But this does happen quite a bit. And it is surprising, polymers actually do like water, a lot of them. Even Teflon has small amounts of water in it, which makes no sense at all. But it is attracted to it enough that it can go in. Is there a question? All right. Does that make sense? Hopefully? All right, entropy is important. Also, structure is important. Okay, and we can actually visualize this. I would like this slide. And so this is showing you polyalpha methylstyrene film, another polymer you won't have to memorize, being dissolved by methyl isobutylketone. And so what we're looking at is this structure of PAMs, the styrene, and the MEIK. And so we start with that result in this three-dimensional NMR scanning, and we're showing the solid and we're showing the liquid. Okay, just like I was drawing a minute ago, but now in much more detail. And so what's happening is these guys are seeing each other across that interface, and as you've already know, the solvent's going to try to go into the polymer, and the polymer is going to try to go into the solvent. And so what you start seeing here is this interface forming in which some of the polymer chains are starting to extend in that solvent. That's where the green color is coming from. And you're also getting solvent going into the polymer, which is where the darker green color is coming from. And then as time goes by, this is 0 minutes, 3 minutes, 6 minutes, 9 minutes. At 6 minutes, that interfacial phase is a fairly large fraction of what we're looking at. And then at 9 minutes, 15 minutes, it's grown even more. And so what you're looking at in this green color is polymer trying to leave the structure, and you can see little bits of green out there and there, where they actually have successfully dissolved and moved out into the solvent. And then you have this region of mixing of the polymer and the solvent at a pretty high level, and there's going to be a gradient in the MEIK that decreases as you move toward that solid. But you can actually visualize this in these structures. And you also see, it's kind of hard to spot, there's a development of curvature, which is the solid reacting to the surface undergoing stress. Okay, any questions about all that? So we understand a lot more about how polymers dissolve, I hope, in this context. And so in the next lecture we'll talk about how these dissolved polymers come together and start providing us with actual large crystals. So we'll see you guys on Wednesday of next week, right? All right.